We are discussing about the electrophiles. So positively charged, yes, they are the electrophiles. What if they are neutral? Consider borane. BH3 is called as borane. Here you can see boron comes with 3 electrons and hydrogen also gave 3 electrons from each hydrogen. But still boron is only having 6 electrons. It is incomplete octet, so it will also act as an electrophile, but it doesn't carry positive charge, but it is a neutral electrophile here. Okay. Right? Now, the another things which could act as an electrophile is diisobutyl aluminium hydride. Isobutyl. That means secondary position of the carbon has got bonded here. Isobutyl. It is diisobutyl. You can see 2 moles are there. Aluminium hydride. Diisobutyl aluminium hydride can also act as an electrophile here. Look at this. 1, 2, 3, 4. To this aluminium has got bonded. Similarly here. 1, 2, 3, 4. To this aluminium has got bonded. You can see the hydrogen are in the bridging positions. So any metal or an element.
But this is bonded to the 4th carbon, right? Not the 2nd carbon.
Yes, yes.
Yes.
So any element which is having incomplete octet is called as an electrophile. Which else can act as an electrophile? Any polarizable neutral molecule. For example, I have chlorine, bromine. If it is undergoing electrolytical cleavage, then that can also act as an electrophile. For example, in Friedel-Crafts reaction, you should have learned chlorine in the presence of AlCl3. Here, chlorine dissociates like this, where this gets a positive charge, this gets a negative charge. Polarizable, yeah, they are polarizable, but still they are neutral one. In presence of a specific reagent, they can act as an electrophile. The molecule itself is polarized on its own, but it is still a neutral molecule when you look at this H plus Cl minus, delta plus delta minus, delta plus delta minus. They are polarized by themselves. They can also act as an electrophile. Clear?
Ma'am, but they have delta plus and delta minus, right? How will
Yes.
they like want more electrons?
See, for example, I have benzene here. I treated any other, let me say, I'm having an alkene here. I treat it with HCl. So this is plus and this is minus. So initially, this double bond would attack this electrophile so that it is creating a positive charge and a negative charge here, because this H plus has went and attacked it, right? So
yes, ma'am.
This is where it is one of the H plus will act as the first part. This is what is called as electrophilic addition reaction. Further, the Cl minus will go on attack it. This example gives you there is a generation of a positive charge as well as a negative charge, where the positive charge will act as an electrophile.
Okay.
Understood? Okay. Now going for the carbenes here. Can carbenes also act as an electrophile? Yes, of course, they can act as an electrophile. We will be discussing carbene in a separate section when we complete the common intermediates of carbons. Okay. Then what else can act as an electrophile? Peracids. What are peracids? Like metachloroperbenzoic acid, which is abbreviated as MCPBA. This will also act as an electrophile. Have you heard about MCPBA?
No, ma'am.
No, ma'am.
Okay. Look at this benzene here. At the meta position, I have chlorine and it is a perbenzoic acid. What is benzoic acid? Benzene, CO. This is benzoic. When I say perbenzoic acid, that means one more oxygen is there. MCPBA it is. Okay, this is also can act as an electrophile here. So these are the list of common electrophiles that will be provided in your question paper. Clear?
Yes.
Yes, ma'am.
Good. Now going for the nucleophiles here. Then if electrophiles are the one which needs electrons, nucleophiles are rich in electrons already. That means they generally have more electron density within themselves. So the common nucleophile will definitely carry a negative charge. Look at this OH minus, CN minus, OR minus, H minus, X minus. They will act as a nucleophile. The very important consideration for a nucleophile. What is a very important consideration? They should be small enough, easy to migrate. They should be small and easy to migrate. Then they will be called as a nucleophile. Okay. Only negative can act as a nucleophile, not necessary. Even a neutral molecule can act as a nucleophile. Look at ammonia here. Ammonia is having a lone pair of electron here. So this can also act as a nucleophile. That means anything which is having lone pair of electron can act as a nucleophile. That's the point here. See, for example, when I have water. Water is having two lone pair of electron. Yes, water can also act as a nucleophile. Ma'am, okay, if water lost in H plus, ma'am, it become OH minus. OH minus can also act as a nucleophile. So a nucleophile doesn't mean it has to be a charged one, can also be a neutral one. Look at this thiol groups. ROH is called as alcohol. RSH will be called as thiol. Thiol means sulfur containing groups. Here they are having lone pair. They can also act as nucleophile. Look at ethers here. ROR. Oxygen is carrying lone pair. This can also act as a nucleophile here. Clear?
Yes, ma'am.
Now talking about the ambident nucleophiles. That means both the sides it can go for pairing up, ma'am. It can act as an electron donor here. Look at this here. Thiocyanides and isocyanides here. R, C and S. I can see the negative charges on the sulfur. If it goes for the reverse, I can see the negative charges on the nitrogen. They are ambident here. They can act as nucleophiles here. Okay?
Ma'am, can you explain
Right?
definition of ambident again, ma'am?
Ambident means there is a possibility within the molecule itself, there is a possibility to have a negative charge on any element. Carbon, it could be nitrogen, it could be sulfur, it could be. That is called ambident.
Okay, in this case, it's ambident because sulfur and nitrogen, they both have lone
Yes,
pairs.
exactly.
Okay.
Okay. Right. So when a nucleophile, 1 minute. Yeah. So the nucleophile would attack the carbonium ion here so that it forms your common reactions like SN1 and SN2 reaction. We will be dealing about all these reactions later. Okay. So the common type of reactions that happens in organic chemistry is only these actually. These 4 reactions only happens throughout organic chemistry. The first one is called as addition reactions. Okay. Since here all are symmetrical, I don't have any domination here, which will go on attack. There is no domination. Priority is not here. So when I have AB, one would become A plus, one would become B minus. So this A attacks this part and B attacks this part. This is where you would have learnt about mark rule and anti-mark rule. Right?
No, ma'am, we didn't.
You didn't learn it. Okay, no problem. I'll teach. See, for example, I'm having CH3, CH, double bond, CH2. To this, you are given HBr. Okay. Now, it is an alkene here. What kind of an alkene? Is it symmetrical alkene or unsymmetrical?
Unsymmetrical.
Correct. It is an unsymmetrical alkene because here, I can see this carbon is bonded with a methyl group. Here, both are hydrogen. It is unsymmetrical. So, the first property that you should know to use this Markovnikov rule is that it should be an unsymmetrical alkene. To that, you are provided a polarized molecule here. Already it is polarized. H plus and Br minus here. Correct now? So this effect, what you are seeing right now is called as electromeric effect. What is electromeric effect? It is basically a temporary effect. What do you mean by that? Ma'am, initially it is a neutral molecule. Doesn't have any charge separation here, but a reagent is coming. And this reactant has to create charge difference so that it welcomes the reagent inside. Being neutral, how can it welcome a polar molecule inside? Tell me.
Could you explain the role of NH again?
NH இல்லடா, அது neutral molecule.
Oh, sorry.
It is neutral molecule. See, for example, you are the guest, you are the host here, some guest is coming to your room, coming to your home. You have to accommodate them. So what do? Okay, I will vacate my room. You can stay in my room. And once the person is going out, once again, you go back to your room, right? Same kind of principle is called as electromeric effect. See, initially it is a neutral molecule, but it has to welcome a polarized molecule inside. So what it happens is that CH3, CH double bond CH2 shifts its double bond to this side. I repeat one more time, CH3, C double bond CH2 it is. So this double bond is shifted towards this side. What will you get then? CH3, CH, CH2 minus. Can I say that?
Yes.
Yeah. Tell me now, why do you write positive on carbon? What is the significance of writing the positive and negative? Does it signify something?
So that the H plus and Br minus from HBr can attack the positive and negative.
No, I'm not asking that. I'm not asking the consequence of it. I'm asking you, I've written positive and negative on it. What does it convey to you? What do you mean by that?
Resonance.
No.
Heterolytic
bond cleavage.
No. What is this positive charge is written? What do you mean by that? I'm asking. Is it the formal charge of the carbon? What is formal charge?
Ma'am, there's only 6 electrons in its octet.
How do you calculate the formal charge? In chemical bonding chapter, you should have learned. What is formal charge? How do you calculate it?
Ma'am, we did learn this, ma'am, but I forgot.
Yes,
Okay,
chemical bonding.
Then no problem. Okay. I mean, you didn't complete the chapter chemical bonding.
No, we completed,
okay.
but then the entire chapter got over in like some 3-4
No issues.
classes.
No issues. Now listen. See, for any element, if you want to calculate the formal charge, okay, take the number of electrons that the element has brought. How many electrons carbon generally brings? 4 electrons, right?
Okay.
Correct?
Yes, ma'am.
Minus. How many bonds it has made? Minus. Number of electrons left out. This gives you the formal charge. Look at this now. Carbon came with 4 electrons. How many bonds this carbon has now made?
3 bonds.
Correct. Is there any electron that is left out on this carbon?
No, ma'am.
No, right? So it's 0. So what's your answer? +1. That's what it signifies here.
Ma'am, how do we know which carbon to choose?
Now I will tell you. Very good. So what is right? Whenever in organic chemistry you write plus, minus, it tells you the formal charges here. This is a very prominent question in JEE. They'll ask you to calculate the formal charges. So the general question is ozone here, where you have ozone like this, right? So they'll be asking you to calculate the formal charges. So you need to know how many electrons, how to calculate the formal charge here. Okay? Now we understood how to calculate the formal charge?
Yes, ma'am.
Right. Okay, now let's go for the mechanism here. And then I will tell you how to design. Which side I should do it. CH3, CH, double bond, CH2. I did the shift so that it becomes CH3, CH, CH2 minus and a plus here. Now HBr is there. Right? Correct or not? So opposite charge attracts each other. This is the only thing that you do in organic. Opposite charge attracts each other. Attracted. Now what's your product? CH3, CHBr, CH3. This is your product, right? What is the name of this product? IUPAC name?
2-bromopropane.
Correct. 2-bromopropane it is. 1, 2, 3, 2-bromopropane. Clear till this?
Yes, ma'am.
Yes. So generally, all the alkenes undergo alkenes, not just alkene, even alkene. That means, in other words, I'll say unsaturated compound undergoes electrophilic addition reactions. Ma'am, bromine is also attacking. Then why don't you say it is nucleophilic also happening? The first attack is happening from H plus side. Then only Br minus comes for the attack. Okay. So all unsaturated compounds generally undergoes electrophilic addition reactions. Ma'am, then benzene is also unsaturated. We have studied electrophilic aromatic substitutions only. There is no addition. That is a difference. Common alkene does not undergo a highly condensed resonance position there. Benzene is highly resonance oriented. So only it doesn't undergo addition reaction. Instead, it goes for substitution reactions. Understood, pa?
Yes.
Ma'am, how do we know which attacks first, ma'am? The electrophile or nucleophile?
See, among the electrophiles and nucleophiles, who is having the faster tendency here? Because it's a double bond. Electron-rich cloud is there. Who will love it? An electrophile or a nucleophile?
Ma'am, electrophile.
Electrophile. That's the reason. Okay. Now going for the question here. Okay, all done. So what have I actually found? Now out of the HBr, the negative part of this HBr, who is the negative part? Br minus. Negative addentum gets added to the most substituted carbon or least hydrogen containing carbon. This rule is called as Mark rule or Markovnikov rule. The negative part of the addentum means who is getting added there. HBr is getting added, means that the negative part is bromine. This gets added to the most substituted carbon of the olefin or less hydrogen containing carbon of the olefin. Olefins means alkenes. But ma'am, will you mean that Markovnikov is only applicable for alkenes? No. Even for alkanes, you can apply it. Understood?
Yes.
Right. So now when I compare these two carbons, which are the olefinic carbons, which is more substituted, obviously, this is more substituted. That is the reason bromine attacked this part here. Now the question arises, how do I know? Why don't I shift my double bond to this side? Shift it. What will you get?
Ma'am, could you say
CH3.
that again, no? For CH3?
Which one, Ra?
CH3, the negative addendum gets added to the carbon with the less hydrogen content. CH3 has
Yes.
the most hydrogen content. So that's why it
Yes.
doesn't.
That's why bromine
Okay.
attached this part. Okay.
Okay. Yeah.
Yes. So the question is, ma'am, in the first case, you push the bond to this side. What if I'm pushing it to this side, ma'am? Since the bond is getting pushed to this side, this gets negative charge, this becomes positive charge. Okay. Why don't I add the HBr like this? Why this is the most important product? Organic chemistry generally doesn't say it is the only product. They always say major product. Why is that? Let's compare. This is my B from the second shift. Right? This is my A from my first shift. Look at the difference that I have. The carbonium ion is in which side? Is it in the secondary position or the primary position?
Secondary.
Secondary. This is secondary. How do I dignify secondary, primary? Methyl cation. This is just called as just methyl carbonium ion. The next one, CH3, CH2 plus, where the carbonium is bonded to only one methyl. So it is primary carbonium ion. Let's for the next one. The carbonium ion is bonded with two methyl groups, secondary carbonium ion. The carbonium ion is bonded with 3 groups, tertiary carbonium ion. Is carbonium an electrophile? Is carbonium an electrophile?
Yes, ma'am.
Yeah, it's an electrophile. It is carrying positive. It is an electrophile. So an electrophile definitely likes being crowded by electron donors. Correct? Can I say that?
Yes, ma'am.
Yes, ma'am.
Yeah. So compare this right now. Here I'm having CH3, CH2 plus, which is connected with the carbon, which is having hydrogens here. This is my alpha carbon, the carbon that is bonded with the carbonium ion. Here, the alpha carbon containing the hydrogen shifts the bond like this. I repeat one more time if you have not learned about this till now. CH2 plus this. Look at this. This is my alpha carbon. This carbon is containing 3 hydrogens here. All the 3 hydrogens are same only. Here, the H plus is going out. If the H plus is going out, this bond pair is still available. So, this bond pair shifts towards this. Now, what is your product? CH2 double bond CH2, an alkene. Correct?
Yes.
Am I right? Okay. So, ma'am, in a primary carbonium ion, there are 3 alpha hydrogens, and there is a possibility one time this could give, second time this could give, third time this could give. 3 alpha hydrogens, 3 hyperconjugative structures are possible here. And this kind of a shift, what you see here, is called as hyperconjugation. What is it called as? Hyperconjugation. When will it occur? Whenever you are having a carbonium ion attached to the alpha carbon containing hydrogen should be. Without hydrogen, you can't go for the shifts there. Clear, pa?
Yes, ma'am.
Right. Okay, what if I'm doing hyperconjugation in this? Here I'm having. Ma'am, this could give, 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 this could give. So totally how many hydrogens you have? 6 alpha hydrogens
6.
you are having. Look at the last one, tertiary. How many alpha hydrogens you have?
9.
9.
9.
More is the alpha hydrogen is directly proportional to HC structures, hyperconjugative structures. More is the hyperconjugative structure, more stable it is. Clear? So that is the reason you say you have to, whenever you're doing a reaction mechanism, you should create a tertiary carbonium ion greater than secondary carbonium ion, greater than primary carbonium ion. Understood?
Yes.
Yes, ma'am.
Right. Now, coming for your question. Look at this. What kind of carbonium ion? Primary carbonium ion. Here, secondary carbonium. Out of them, which is more stable?
Second.
In inorganic, whenever you say it is very stable, you say it is least reactive. Organic is just the reverse of it. When I say it is the most stable intermediate, then you say it is the most reactive here. Since it is the most reactive here, I should not go for this shift. Instead, I should go for this shift only. Clear now?
Yes, ma'am.
Is it clear? Both of you?
Yes, ma'am.
So this rearrangement or this shift is what is called as Markovnikov rule, where you do to replace the electrophilic reagent, the reagent that is getting inside to that, you form a product where the negative atom gets added to the more substituted carbon of the olefin. Okay. Right? So where were we actually? Right. If you find me going faster or if you want me to repeat anything, you can ask me, of course. Okay. Do you get my point here?
Yeah, yes.
Yeah.
Yes, ma'am.
Right. Now going for the elimination reactions. Now, what is this elimination reaction? Here, we are very much concerned about a thing called as leaving groups.
Ma'am,
What
what
is
is
a very...
anti-mark reaction, ma'am?
Okay. Which screen are you able to see? My document?
Yes,
What
ma'am.
document?
Where you have
Yes,
written
ma'am, your
mark and
document.
anti-mark.
Okay. So we are looking at the anti-mark rule now, right? Right now here. So what is this anti-mark? See, in case I'm adding the same reactant, to this I had HBr in the presence of hydrogen peroxide, which is also called as peroxide effect, which is also called as Karash effect.
Ma'am, are you writing anything on the screen?
Yes, Dad, that's what I asked you. What are you able to see?
Now we can't see the screen, ma'am. You can only see the PDF that you showed us first.
Now.
Yes, ma'am, now we can see.
Yes, ma'am.
So anti-Markovnikov rule is also called as peroxide effect or Karash effect. Okay. Now, what is this effect is telling you? Just the reverse of it. The negative addentum gets added to less substituted carbon of olefin or more hydrogen containing carbon of olefin.
Ma'am, this will only happen in the presence of H2O2.
It will only happen only in the presence of peroxide. It is not just H2O2, any peroxide. Even if you are going to give like this, any peroxide it could be. In general, you can remember peroxides are nothing but whichever is having this OO bonds like this. Anywhere, whenever they are giving benzoyl peroxide or hydrogen peroxide, there and all, the reaction will happen like that. Now, what is the mechanism of this reaction? Markovnikov rule was going with respect to carbonium generation in the reactant here. Here it is going for a free radical mechanism here. It goes via a free radical mechanism. Now let's see the mechanism. How does it happen? See, initial, let me take any peroxide here. As I said, free radical mechanism. When will a free radical be generated? In homolytic or heterolytic cleavage?
Homolytic.
Homolytic.
Obviously, homolytic. So break it in the middle. So what you get is 2 RO dot. Because it takes 1 electron each, right? Now it's a free radical. So this RO dot goes and reacts with HBr here. So here also the homolytic cleavage happens. H dot, Br dot, bonded. ROH and Br dot. Again, you created a free radical. Now this Br dot is going for your reaction. H3CH double bond CH2. Now break this double bond here, homolytic. Can you see this? Right.
Yes, ma'am.
Now, ma'am, I can see what if this Br dot is going to react with this dot? CH3CHBr, CH2 dot. One H dot should be there. Why don't it again give the same mark product itself? If the Br dot is reacting with this dot, CH3CH dot, CH2Br, this dot would react with an H dot to form CH3CH2, CH2Br. You said only this product is a major product here. This is minor here. Why? I am seeing equal possibility here. Again, I tell you, organic reaction mechanism goes with respect to the stability of the intermediate. What do you mean by an intermediate? It is never seen in a reaction coordinate diagram. When you see a reaction coordinate diagram, you can never see them. They are very short-lived, but they decide the fate of the product. Look at this. What kind of a free radical you generate here? Is it a primary free radical?
Which one, ma'am?
Huh? Is it a primary free radical, Pop?
Yeah, yes, ma'am.
Yeah, it's a primary free radical. What about here? What kind of a free radical?
Secondary.
It's secondary, ma'am.
Secondary free radical. Now, we discussed about the carbonium ion. We said it is carrying positive charge, so it's an electrophile. What about this carbon free radical? Does it still need one electron to satisfy its valency?
Ma'am, could you repeat that?
I'm asking you, carbonium ion, we said it is an electrophile because it is carrying a positive charge. Correct? What about the carbon free
Yes.
radical? Does it still more need one more electron to satisfy its valency?
Yes.
Correct now? How did you generate an radical? I just broke it in the middle so that each got one electron. That means each of them needs one more electron to satisfy their valency. Correct? So can I say this is also an electrophile?
Yes.
Yeah, it's also an electrophile. So carbon free radical follows the same stability trend of carbonium ion. Carbon free radical follows the same stability trend of carbonium ion. Now you say, which is more stable, this or this?
The first
2
one.
degree.
2 degrees. Secondary. This is more stable. That is the reason this is
Oh,
your major product.
ma'am.
Hmm.
Oh, wait, sorry. In the first one, it's a primary free radical on the right side.
Primary.
Yes.
Yeah.
Ma'am, one more thing, ma'am. Unlike the first Markov-Nikov addition, where H plus also got, I mean, reacted with the negative charge, and then and then formed the bond. Why isn't that happening here? Only Br minus is getting added.
There is no Br minus at all. Br dot only is getting added here because that H dot reacted
Yes,
with
ma'am.
R dot here.
Okay. Yes, ma'am. Got it.
Now the common competitive question is, will this be happening even if I give HCl in the presence of hydrogen peroxide? HI in the presence of hydrogen peroxide? No. Because only HBr follows anti-Mark II. They all do not follow this. The reason is, in this reaction that you see with HBr, the reaction totally is exothermic in nature. Complete reaction is exothermic. Organic chemistry generally loves releasing energy. Why do you think so? Why they love releasing energy? Because any
To
system,
become more stable.
exactly, why do you say that? Good. They become very stable by releasing energy. That means they want to go to the lower energy state. So any system in the universe, if you see, they always want to go to the lowest energy level. That is their stability. And that's the reason HBr only follows AM rule. In the case of HCl and HI, they are not completely exothermic. One of their first part or the second part, they are a combination of endothermic and exothermic reactions. That's the reason only HBr follows AM and HI and HCl will not. HF is no question at all. HF never comes for the reaction.
Yes, ma'am. Ma'am, can you scroll a little bit up
Yes.
for the previous one? Yes, ma'am. So after CH3, CH5, you have the secondary free radical. The original H free radical reacts here to
Reacts with
form
it. Yes.
CH2. Why
Yes.
doesn't the same thing happen in the first one?
Just now I told you that. In the first one, we are
No,
just
ma'am.
looking
You
at
said that the H dot will react with RO to form ROH, but there'll still be one more H dot remaining, right?
that means HBr is in excess. It is not like 1 mole equivalent. They are providing you in excess.
Okay. Okay.